Greetings, building science enthusiasts, and welcome back to the Building Science Podcast. This episode is brought to you by the Humid Climate Conference. Back in 2015, the Austin chapter of Passive House Alliance US was thinking about how to get more attention to the FIAS Plus 2015 standard in humid climates. And so the thought emerged, what if we put on a conference? I'm proud to tell you that this is an unmissable conference. It's a unique gathering of the best building science minds who are ready to talk seriously about passive house and humid climates. This event is entirely volunteer organized, supported by Passive House Institute US, and sponsored by some of the best product manufacturers and industry consultants in the country, and it's sold out in its first try. But it's happening again this year, May 21st and 22nd, with a great speaker lineup. We're talking Joe Stiebrick, Lou Harriman, Richard Corsi, Matthew Tanteri, and the list literally goes on and on and on. Find out more at humidclimateconference.org. Early bird tickets are limited and they're selling quickly, so don't miss out and be left wondering. Register today. That's humidclimateconference.org for tickets. Now sit back, relax, and enjoy the episode.
Welcome to this. Welcome to the
Building Science
podcast.
Welcome to the Building Science Podcast.
Bringing the human factor to architecture and design.
Brought to you by Positive Energy in Austin, Texas.
Hello and welcome back to the Building Science Podcast. I'm Kristof. I'm here at AHR with John Miles from Sanden. Sanden is a heat pump water heater manufacturer that relies on a CO2-based refrigeration cycle. And John, please introduce yourself.
Hello everyone, my name is John Miles. I'm the general manager for Sanden water heaters here in the US, or North America actually we should say. And we're selling the Sanco 2 CO2 heat pump water heater. It's a really unique take on heat pump water heaters, driven from the Japanese EcoCute, and I won't butcher the Japanese way of saying it.
What's that mean, EcoCute?
EcoCute, so Kyutaki, which in Japanese basically means Kyutaki, right, or Kyotaki, or whatever, however it's said, and my Japanese accent's appalling, basically means hot water.
Oh, really?
And eco means echo, right? Economical is echo in any language, right? So the real name for this is Shinsen Ribai Hitopompo Kyutaki, which means essentially hot water heat pump in Japanese, and everyone has shortened that name to EcoCute, and it's the genre of products that were basically introduced into the Japanese marketplace sometime between 1999 and 2001 as a collaboration between the Japanese government, industry, and the educational facilities, Tokyo University, to design a product that outside of the urban areas of Japan, and we're all familiar with Tokyo, Osaka, and the big urban centers of Japan, but outside of Japan it's very mountainous, it's fairly rugged and rural, and they don't have a huge amount of infrastructure in terms of natural gas moving out beyond the cities and beyond those urban areas. So electric water heating was very expensive. Japan, as most people probably are aware of, is a nuclear power generating area. They don't have much in the way of coal-fired resources or natural gas resources of their own. So electricity's always been expensive, and they use a lot of hot water. They're actually very Americanized in that scenario because they enjoy the bathing culture, right? Where, yes, you have your shower, you get clean, but then you draw a 60 or 70 gallon bath to basically sit down and relax after your hard day slaving away as a salary man. And you sit in the bath and you contemplate this. And so they wanted very hot water temperatures and a lot of hot water capability to create that, and they wanted to do it
electric and
efficient. So heat pumps were sort of the game. I mean, heat pump water heaters have been around since the 50s, but
Are you serious?
Yeah, I mean, the first patent for a heat pump water heater was filed in the US in 1953.
Right on. But why are they're still not mainstream in the U.S.?
Oh.
And I'm just learning from you that it's a cultural and an energy cost basis that drove the Japanese this direction. I didn't know that.
Yeah, so unfortunately, water heating, for many, many reasons, here has become a first cost issue, right?
Yep.
Whether it's first
not
cost,
just water heating.
it's not just water heating, right? Because at the end of the day, the one thing that's interesting about the US world is that you have no idea what each of your appliances cost you a year to run, unless you wanted to put amp meters on everything and say, oh, wow, it cost me literally $600 or $700 a year to run my electric water heater. Maybe there's a better way of doing it, whereas it fails and it's like, oh, I just need to run to Home Depot or call my local plumber and put exactly the same thing in, and I don't have any clue that over its lifespan it costs me $10,000 a year to run if I do 100 gallons of hot water a day, which is pretty easy to do in a 4-person household.
60 to 120. So actually, let's tell the listeners that. So the electric water heater. Let's talk about efficiency. What is the electrical efficiency, or the water heating efficiency of a typical electric resistance
It's
water
below
heater?
1. I mean, it's typically 0.96, 95, something like that.
So 96, 96% efficient.
You put a kilowatt of energy in, which costs you 20 cents, 10 cents, whatever your kilowatt hour rate is, and you get 96% of that out
in hot water.
In hot water.
And that sounds pretty awesome. But then, I mean, it does. 96, if I got 96 on an exam, I'd be like, woohoo, back in school. But so 96% efficient something, it doesn't sound bad. But tell us about these heat pump water heaters.
Well, that's the great thing about heat pumps in general. I mean, whether it's a water heater or anything like that.
Or space heater.
Yeah, space heating or all of that. So, for example, with our unit, if you put 1 kilowatt in, I can get you 5.2 kilowatts out. So that's basically, you now scored 520% on your exam, which I think gives you an A+++, right? Or something like that.
Teachers I think I cheated.
Yeah, right. I mean, like, that's knowing the answers and the extra credit work, right?
So how does that work? How does it get to 520% efficient?
Well, so essentially what we don't do is we don't have this amazing machine where we create energy from nothing. Because the unit is...
We don't.
No, unfortunately not. So we put a kilowatt of power into the compressor, into the refrigerant, and what that allows us to do is draw the extra energy from the atmosphere outside. So when it's 50-odd degrees outside, there's heat available for us to steal that heat from outside.
From the air
outside, put it into the refrigerant, and then ultimately into the water that we're trying to heat on that particular system. So that's how we get the energy bonus on that.
Okay, and so I happen to know that on that same exam, most of the American heat pump water heaters would get about a 250% score.
Yeah, they get 2.5 to 3.
And
right?
those are COPs, by the way, coefficients of performance, 2.5. But it's referring to efficiency.
Yeah, I mean, a COP is essentially a calculation of capacity out divided by input in, right? So it's a very straightforward calculation. It's a dimensionless number.
So why is it that the US ones are getting like 2.5 and you're getting 5?
Well, I mean, so we've packed ours with as much technology as we possibly can. So our compressor, for example, the US uses what we call a fixed speed compressor, where it runs at one speed whether it needs to or not. The Sanden unit uses a variable speed compressor. So essentially, we can look at the US product. If you take that analogy to your automobile, it's like going everywhere with your throttle or your accelerator pedal flat on the gas, right? And you go everywhere at 100 miles an hour or flat out. Whereas with us, it's like putting your foot on the gas and just drawing along quite nicely, at a steady speed, depending on road conditions, etc., like that. Whereas, so we can reduce your gas mileage or reduce your energy consumption and improve our COP
you can
from that.
Increase the mileage.
Yeah.
So you said there's a lot of technology in here just then. How's the reliability on these units?
It's actually pretty amazing, to be honest with you. I mean, there's a lot of technology, but it's technology that we've been familiar with for 15 odd years in the Japanese marketplace. Sanden is one of those companies that, even though the brand name may not be familiar, we provide the compressors for 25% of the world's automobiles that are manufactured today.
Oh, really?
We count our failures in like decimal points per million of compressors. So,
decimal points.
Yeah, because those are what the manufacturers, the auto manufacturers like Mercedes and BMW and some of the other the brands, they all require. So, our efficiency, our reliability performance is pretty amazing, and we back that with a industry best warranty anyway. So
that's super cool. So, variable speed compressor. There's also refrigerant difference, right? And that makes a fundamental change. Is there a simple metaphor or a simple way to talk about that?
So one of the in a roundabout way, no. One of the things with the American units or the US style product is it has to live inside of the house or a space for it. Typically it wants to see ambient temperatures no lower than 35, 40 degrees Fahrenheit, because the one thing about stealing the heat from the air is that the end result of that is, yes, you get that warm water, but you also get cold air being blown off it. The way that the refrigerants are designed with the other units is they're good at doing that only to a certain temperature point. Whereas what we have picked for this reason, and the reason that the Japanese market wanted it, they wanted the unit outside. It gets cold in Japan. They wanted to have the ability to make hot water when it was cold outside. So we went way back into the history of it and went to one of the original refrigerants, carbon dioxide. It was actually back in the 1890s. It was a very popular refrigerant until people started synthesizing the synthetic refrigerants that we used to use. So CO2 has this innate ability, we can go and do a high school physics lesson or chemistry lesson and talk about it, but it has this amazing ability, even when it's minus 10 outside, 0, whatever, of making 165 degree hot water. So it just really has this amazing ability to capture any heat, even when you think there's no heat available because it's freezing outside. Capture that, put it into the unit, into the water, and get that water temperature up nice and high. So it's one of the great things about our unit.
So how cold can it be outside and this system still run okay? I mean, because at some point it gets too cold out, right?
Well, not really. I mean, there's always heat. So we have these units running below negative 20.
Woo! Negative 20.
And making
Fahrenheit.
Negative 20 Fahrenheit.
Wow.
And making 160 degree water.
Wow. That's amazing. Okay, so it's using CO2 as a refrigerant. The unit is outside. So that's a benefit right there. The tank can be either inside or outside, is that right?
Well, I mean, the tank lives wherever you want the tank. I mean, most of the time you want it inside. Well, it's not just that. It's also about plumbing, right? This is a system, right? So you want the tank as close to the major use of hot water that you have, whether it's the bathroom or whatever it is, because, it's that age-old thing where you stand in the shower and you're waiting how long for your hot water to arrive. Well, the closer the tank is to that, the shorter that does, unless you go for a recirculation loop. So it's a system-style thing. So the idea with the tank is that it can go. They're very compact. They have very little clearance requirements, so they can go, for example, we did a 30-unit apartment block in Seattle just recently where these go in a closet under the stairs, and you couldn't do that with a normal American-style heat pump water heater.
Right.
So
because the compressor is attached to it.
Because the compressor is attached to it, it needs airflow. It needs 100 cubic feet to breathe properly. Whereas with our unit, the heat pump being outside, the tank...
It's more like 850 or 1,000 cubic feet, something like that.
Yeah. So 10 by 10 by 10, right? So it needs that area to breathe, to get the air in and out of itself. Whereas our tanks just sit around and kind of look pretty. And
So we're actually, this sound right here is, we're doing this interview on top of a tank. So this is a how many gallon tank?
this is a 43.
Okay, and I'm like 6'2", and it's up to my belly or something. Yeah. And so what runs in and out of this? Is refrigerant going in and out of this?
It's a water tank. So this is manufactured. This is actually a little bit different to a normal water heater tank that you're probably familiar with. It looks the same, but under the skin, this is actually stainless steel.
Wow.
So it's not a glass-lined enamel, which is sort of the normal, and that's why they fail, because the enamel eventually cracks and the rust gets in behind it, and away
But
it
it is
goes.
first cost optimized.
Yeah, I mean, I will give you that. I mean, stainless steel is not a cheap solution for us, but it's a better solution.
Yeah.
So,
And how, I mean, there's got to be some restriction on the length between the outdoor and indoor. Like, you have a water line running in. Okay, so the water line has to be very well insulated.
yes. I mean, so there's a
If it's minus 20 out, then I got a hose.
Yeah, I mean, we insulate the water line with an inch closed cell armor cell, which is readily available. When the temperatures are low, we also put a self-regulating heat tape on it, which is basically like a little electric heater that draws about 8 watts per foot. We have a really intelligent one that's manufactured by Raychem. It has the ability to vary its heat output every inch.
Wow.
It's pretty amazing. Doesn't look very amazing when you look at it. It's just a black cable, but the technology involved is pretty good. So yeah, we insulate. The unit has its own freeze protection program set up, and as you say, it can be about 50 feet away from the tank.
50 feet away. And so that water line goes from the outdoor unit, the heat pump unit, and it goes straight through the wall, or does it go inside? How does it usually work?
Well, it's a myriad of different things based on that, but typically the typical installation would be that you'd set the outdoor unit outside.
Can it be wall mounted outside?
Yes, yeah, it can. It can live up on a bracket. You can hide it behind a deck or behind a bush or whatever it is. Typically, you'd then core about a couple of inch hole between in the wall. Snake your 2 water lines in between there, and there's a temperature sensor that runs between the tank and the heat pump that controls the heat pump operation.
So that's a wire.
It's a wire, yeah. And basically, when the tank gets cold, it tells the outdoor unit to start the pump in the outdoor unit and to bring the cold water from the tank to be heated, and then drop that hot water back into the tank.
Okay, interesting. So I see a bigger tank over there. How big is that tank?
That's 83.
83 gallons.
And we're also going to come out with 119 gallons here, mostly aimed at the light commercial marketplace.
I can see that, yeah. Multifamily.
One of the other kind of weird things you can do with our unit, maybe not weird, but is there's nothing to stop you putting 2 units on one tank. So each one of these units creates around about 20 gallons an hour of hot water. So if you have a high usage scenario, say it's a school kitchen or a restaurant or fast food or a light commercial style application, you could put 2 heat pumps on to one tank, which is why we're going for the bigger tank, and then you can deliver maybe 130, 140 gallons of hot water out of that tank and make it up at 40 gallons an hour. So you have some flexibility with our systems, and we use that in some multifamily work, in some light commercial operation and things like that.
Makes sense. So the 160 degrees is pretty hot. I know most people aim for 120 to 140. Is there an anti-scalding situation? I mean, how do you handle that hot water?
So actually, 160 is kind of low range for us.
Really?
We can take this unit up to 175. If I wanted to take the brakes off, I could get 194, but we govern it to 175. So you can set the temperature outside depending on your personal preference.
You set the water temperature at the outdoor unit?
At the outdoor unit, somewhere between 130 and 175, depending on...
Oh, I see. So you don't have to set it. It doesn't it makes 160 degree water, but it can be diluted down to whatever temperature you prefer.
Yeah, and then when we provide the units, it comes with an anti-scald valve, which then you dial down to 110, 115 for your normal bathing habits, right? So the reason that you do the higher water temperatures is depending on your individual user preference or user hot water profile, you may want to say, I'll make some hotter water and store it as a thermal battery in the tank, especially if you have, for example, photovoltaic on your roof or something like that. During the afternoon when the sun's shining, you can take all that energy, push it through your photovoltaic panels and store it at 170, 165 degrees in the tank as thermal energy, and then use that thermal energy, bleed it out through the night and through the morning rush, ready to replenish during the afternoon. So
because you can always mix it with the cold water.
Yeah, and that's exactly what the anti-scald valve does that we provide with the system. You know, because most of the time you're going to take it out at 110, 115. But if you have this 43-gallon tank full of 160 degree hot water, you mix it with 45 or 50 degree cold water incoming, you're only, for every gallon of hot water you only use about 0.6 gallons out of the tank.
Right on, that's cool. So thinking about the numbers you started out this interview with, where we said it was like roughly 100 gallons a day is roughly $600 a year for hot water. Are those legit numbers? I mean, you've gone through some math on those?
Yeah, I mean, we've done...
I'm curious how that would relate to dollars per year for one of these in that same situation.
Yeah, I mean, we put some numbers together with the help of Washington State University, who've done some extensive research on this, and there's been a lot of research done up in the Northwest on heat pump water heaters and water heating in general in terms of cost, because, you know, if we look at the Northwest itself, there are 2 million electric water heaters up there, just in sort of Seattle, you know, Washington, Oregon.
They don't have natural gas distribution up there? Oh, they have hydroelectric, right? Is that one of the reasons?
They have that. They have some wind, but it's just historically been outside of Seattle, and it comes back to that analogy we made right at the start, where it's Japan, right? And it's outside of the urban areas. You're sort of off the natural gas grid, right? So everyone's gone to electric water heaters or maybe some LP ones, and the utilities up in the Northwest now have been looking at the Japanese model, and it's like, how do we replicate that and reduce our overall grid? Because you remember that, you know, we talked early in the podcast about the fact that you've got a 1 kilowatt in on an electric water heater and 96 kilowatts out. Well, a typical electric water heater has a 4.5 kilowatt element in it. So every time that element fires to make that hot water for you, you're firing at 4.5 kilowatts. So that's, you know, at 10 cents a kilowatt, it's 45 cents. At 20 cents, it's 90 cents. And it's also a big load on the grid. So if you imagine those 2 million electric water heaters all turning on at once, that's a lot of electrons having to fly down, a lot of transmission lines. And if we said, okay, you replace all those with Sandom, which would be absolutely spectacular for me, you know, I can take that 9 million kilowatts that we just did, and I can take that down to 1 million kilowatts, because, you know, or 2 million kilowatts, because I've got 2 million units all burning 1 kilowatt. So it's a 4.5 times reduction.
So there's a societal level benefit, right? Because you don't have to invest in the grid, you don't have to maintain the grid, you can take peaker plants offline.
Yeah, I mean, and they have, certainly, you know, I can speak a lot for the Northwest because we do a lot of work up there, you know, is that they can now shut down coal power plants, they can go to wind. You know, one of the things that we've got with our units is what we call a demand response program, where the utility's got too much electricity, can fire our units up, store that electricity as hot water, as thermal storage, as thermal batteries, and that's something that they're really interested in doing. They always have a glut of wind power at like 4 a.m. when nobody's actually using electricity because everyone's still in bed.
That is so cool. That is super, super cool.
So you look at it and it's like, yes, it's one little device, but if you kind of like just keep pushing yourself down the rabbit hole, there's this huge ripple effect that goes all the way up to how we generate power in the future.
Okay, so this might be outside of your technical expertise, but we got to get these devices into homes, and that means we got to go to the people that make the decision on what am I going to do for water heating. And typically, it's actually not the homeowner; it's usually the installer. The homeowner's like, my water heater broke. The installer says, no problem, I'll install whatever I decide is best, and that's usually whatever I know. What can we do as a society to get the installers to recommend heat pump water heating?
Well, that's kind of the reason we're here, right? I mean, there's 65,000 people come to this show.
Yeah, this is crazy.
Now everybody stops and says hi, but I spend personally a lot of time out on the road training contractors, training our distributors, teaching them how to do this unit and why they want to sell it.
Do they like it once they understand it?
Yeah, I mean the typical, it's kind of like the ads you see in the airplane magazines for the 8-minute exercise machine, right? Where you see it, you don't understand it, then you look at it, and it's and then they put the first one in, and it's holy XYZ, right? This thing just, I can't believe it works so well.
It's so easy.
Yeah, right, and how easy it was to install because it's just water lines, a little bit of electric power, and off you go from there. So, it's, I don't want to say when you do your first one you never go back, but that's kind of the program that we like to work on, right? So,
all right, well, thank you. I think that's a lot of good information for people to hear, and I appreciate it. And I think it's fantastic. Societal level benefits from one little machine like a water heater. Thank you, John.
Yeah, I mean, we didn't even talk about the low global warming potential of CO2 either.
Oh, let's talk about that let's wrap up. Tell me about that.
I mean, that's one of the other benefits of CO2. Not only is it the best fluid for us in an economic point of view, for getting the best bang for the buck out of the unit, making that hot water, doing it as efficiently as possible. There's this little thing called global warming potential, right? Refrigerants, the state of California is, to paraphrase them, has determined that refrigerants are a short-lived pollutant, because their global warming potential. So our competitors use R134A and R410A. So 134A has a global warming potential of 1430. R410A has a global warming potential of 2086. What that essentially means is that if I had a pound of 410A in my pocket and I just opened the canister and let it all fly out into the atmosphere, over the next 100 years, that 1 pound of 410A will do the same amount of damage as releasing 2,086 pounds of CO2.
Oh my gosh.
Right? And we all know that CO2 is the metric that we use to determine pollutants. If I did the same with the 134A, it's 1,430 pounds over a 100-year period. Okay. Right? If I released the same amount of CO2 because it lives in the atmosphere with us, it's what we call a natural refrigerant, it's got a global warming potential of 1. Mm-hmm. So it's a magnitude of 1 2086th of damage to the atmosphere if it was to leak out of the system. And everything has an end-of-life program. Well, it's all supposed to be recovered and things like that. There's an end-of-life cost or a leak cost occasionally on these systems. So it's a natural refrigerant, it's a low global warming, so it has an environmental impact on that point of view.
I get it. And not only that, but you're taking out the CO2 from the atmosphere and you're sticking it here in your compressor. A small amount, I'm just kidding.
Well, yeah, you laugh about that. It is a byproduct of another operation, so it's not something that people spend extra time. So if the people that distill pure oxygen out of the air end up with pure CO2 as a byproduct, so we take that as our refrigerant, we call it R744. So it's not something that you have to spend a special amount of time doing. And
Now that you've said that, it gets me thinking, okay, so why is it that why are we using 134A and 410A and not CO2? There must be some downside to CO2, something harder about it, or...
Well, I mean, at the end of the day, what we look at is it's a cost, right? I mean, it's at the end of the day, we can play that first cost ROI payback game, right? And CO2 is technology that unfortunately the rest of the world has embraced significantly. Japan in particular, being very, very environmentally conscious, and they're using it all over the place. They're using it not just in the water heaters. There's 500,000 of these types of water heaters sold every year in Japan, but they're using it in refrigeration systems. All their 7-Elevens and convenience stores are starting to move to CO2 refrigeration.
But what about in this country?
Slowly, you're seeing the companies, Whole Foods and some of these other guys move to CO2 refrigeration, but they're again balancing that capital cost against, against the cost of the additional.
Does it balance out over the lifetime of ownership?
Oh, certainly. Depending on your water usage, we can pencil out anywhere in a payback period against electric or an LP gas water heater in the low 2 years, maybe 3 years, something like that.
Yeah, that's incredible. Yeah, the United States as a consuming society, consumer society, we really are fixated on first cost instead of the service. This is the thing that's going to provide a service to me. And so there's the cost of putting it in my house and the cost of using it at my house. We really need to be thinking more about long-term costs of ownership.
Yeah, it's funny. One of the guys from our distributor up in the Washington State area, he says to me, I've lived in my house for 30 years, and the reason I know that is I've replaced 3 water heaters over that time period, right? Because, I come home and the basement's full of mildly warm water, right? And I put, we essentially take that one out, put a new one in, and it's exactly the same one year after, time after time. It's one of those weird products that water heaters, we expect them to fail at some point, whether it's 6 years in or it's 8 years or 10 years in. And we all rush off like lemmings to the Home Depot and get exactly the same thing without thinking like, hold on a minute, how much did this actually cost me over its lifespan to run?
Thank you again, John. Fantastic interview. And thank you guys for listening.
Thank you very much. Really appreciate it, Kristof.
You're a natural, my friend. Have you done that before?